Okay, so here we're going to take a look at transition diagrams for our Turing machines. All right, so similar to our DFA diagrams, states are going to be the nodes and transitions are the directed edges. All right, now each edge, right, will be labeled with the sigma tau d, right, where sigma is what is red. All right, so what takes in, tau is what to write. All right, and then here D is to move in the direction, either left or right. Okay, so no double circles for any kind of accepting state. The only special state is the halt state, which has no outgoing edges. All right, and then in the textbook it says that it writes the same symbol, so any omitted transition, right, defaults to write the same symbol, move right, and halt. Right, so something shows up that that was not expecting, it moves to the right and it just halts. So we'll take a look here at a simple machine here, example from the textbook, right, where it swaps A's and B's until it finds a C. Okay, so from Q0, okay, so let's say that we start with an A. So we read A, we change it to B, and then we move right. Okay, so again, read A, right, B, move right. Okay, now all of these are going to have the same idea here, so we really can just, since there's no memory, we don't need to know what came before, we don't need to keep track of anything, we can simply stick with this one state. All right, so we can, the other possibility is I see a B, flip it to A, and then again continue moving right. Okay, so again, read B, write A, move right. Okay, and then also here we could blank blank, do nothing, and continue to the right. All right. And then lastly, we could encounter a C. C, C, L. So here it reads a C, writes a C, and then move left. And then here is where I wanted to stop, so here go to H. Okay. So the way this would look is we'd have Q0. All right, and then from here, right, we have three kind of loops back onto Q0. All right, where we have here A, B, R, B, A, R, or blank blank R. And then if it comes across a C, you get C, C, L. And this is RH, right? Halting state. So notice that once it's there, it halts. There is no outer edges. There's nothing else to do here. All right, so that is what our transition diagram does. Now here is a visualization of it, a better visualization than just the diagram here, and we can actually run it here, run it on a sample string here. One thing I notice okay, so here we go, right? Okay, so here you'll notice we have the Q naught, and then it has all those transitions, right? A, B, R. Okay, here it looks slightly different than our notation, but it says A replaced with B, B replaced with A, etc. And in all cases, it's moving to the right. And as you can see here, we'll do one step at a time. You see, changes it to B, changes it to B, A, encounters a C, moves back one, halts. We are done, right? Try to do one more, and I am in the halted state, or the halting state, so it does not move from here, right? Now, here's another Turing machine. It does the same thing, but it keeps track of odd or even, and we could see it's just it's not necessary since I don't really do anything with that information, whether I'm in an odd position or an even position, but it works exactly the same way. You see? So here, right, as long as, we don't need to remember anything, or the machine doesn't need to remember anything or back to anything, then we don't need to add any additional unnecessary states. Okay? All right, so that's a basic example here of our Turing machine and a diagram, right, and how to read it, right, so how to interpret those here. All right, now to kind of wrap up this section here, all right, we want to talk about what are called Turing computable functions. So a function f that goes from sigma star to gamma star. So a function of like this is called Turing compatible. If there is a machine for every input W, M halts with output FW. All right. Okay, so the example from the textbook is that we have A to the N, A to the 2N. Right, so here it doubles the number of A's. All right, so there is a Turing machine that computes this. Okay, and so here, previously when we discussed DFAs, well, we only talked about computations on strings, right? Well, we didn't talk about computation. We just looked at the recognition of the string, and we're looking for anything in particular. A Turing machine actually computes, right? Whereas opposed with our DFAs, right, all they did was decide whether it was a valid output or not. Okay, so when dealing with Turing machines, there are two notions of language computability. So we can compute, so two ideas behind the language computability. The first one is something called Turing decidable. So what that means is that the language L is decidable if there is a machine M, right? So L is decidable if there is an right, a machine that for all W element of the strings, M always halts. All right, and that outputs 1 if W is an element of L, and 0 if W is not an element of L. So the machine always gives a definite yes or no. So that is Turing decidable. Now on the other end, there's Turing acceptable. So L is acceptable if there is a machine M such that M halts on input W if and only if W is an element of L. Now, if the string is not in L, M may run forever. The machine can say yes by halting, but it cannot say no. It just keeps running, which is the main difference here. Okay? So decidable language, you always get an answer, right? An acceptable answer, right? You may get a yes, but you're not sure if it's there or not, right? It may keep running forever. So every decidable language is acceptable, but the converse is not going to be true here. Okay, and we'll talk more about one that may be decidable, acceptable, but not decidable. Hold on, just keeps running. Every decidable language is acceptable, but not vice versa. Okay, if it is acceptable, it is not always decidable, right? So decidable does imply acceptability, but not the converse is not true. Okay, and we'll take a look at examples of that in later videos. Okay, but for now here, what we want to get here is we're able to read the transitions, the diagram, and decide the labels, read what it's doing, and recognize when a machine halts.